Hello, statisticians. Mr. Youngsaver here from Skew the Script. In the decades following the introduction of the measles vaccine, measles was declared eliminated from the United States. However, in recent years, we've seen an uptick in measles cases. Today, we're going to explore one factor that may be a driver of this phenomenon. Let's skew it. Today's lessons on problems with intervals and tests. Measles is a viral infection that's most common in children, and in 1910, the United States had about 6,000 measles deaths per year. By the 60s, the United States had about 3 to 4 million cases per year. But then we had a breakthrough. In 1968, the modern measles vaccine was developed. By the year 2000, the WHO declared that measles was eliminated from the United States. However, recently, we've seen an uptick in the number of measles cases in the United States. 2019 had the greatest number of measles cases since the early 90s. According to the CDC, many of the outbreaks could be traced back to clusters of unvaccinated individuals. So this raises the question, why are parents choosing not to vaccinate their kids against measles? Well, one possible reason is research published by this man, Andrew Wakefield. He was a British doctor who published a 1998 paper linking the measles vaccine and autism. His research set in motion a long-lasting wave of vaccine skepticism, and that skepticism contributed to low vaccination pockets in states like Oregon and Washington, which had pretty substantial measles outbreaks in 2019. So today, we're going to use the tools of statistics to analyze, do vaccines in fact cause autism spectrum disorder? If you'd like to follow along using guided notes, you can print them out on our website. So first, let's discuss bad study design versus statistical error. Wakefield published his study in 1998 in The Lancet, which is a British medical journal. In the study, he examined 12 children that were referred to his lab with autism or related disorders. Like most children in the United Kingdom, all 12 of the subjects had received the MMR, measles, mumps, rubella vaccine. Using this as evidence, Wakefield suggested that there may be a vaccine autism link. In other words, because all 12 children had autism-related disorders and all 12 had had the vaccine, Wakefield suggested there might be a link. So people across the globe then use this study as evidence that vaccines cause autism. Well, as statisticians, we know that to establish a causal link, we need a well-designed experiment. And by that, we mean that we need the experiment to meet these 4 principles of experimental design: comparison, random assignment, replication, and control. So let's examine if this study meets these 4 criteria. First, starting with comparison, there wasn't really any comparison in this study. Wakefield did not compare the patients in his lab to non-vaccinated patients. And non-vaccinated patients also develop autism spectrum disorder. He also didn't randomly assign treatment. He didn't randomly assign the subjects to get vaccinated or not. He just studied children in the lab who, like most UK children, had been vaccinated and were just referred to him. He also only studied 12 individuals, which isn't a very high sample size to be looking at to meet replication criteria. And the biggest one of all is that he didn't control for any confounding factors. Yes, all 12 children were vaccinated, but they all also have probably slept in a crib, crawled on carpeted floors, fallen asleep on their back, worn clothes made of cotton. Do vaccines cause autism? Or do one of these other factors cause autism? Or do any one of thousands of other potential factors cause it? There is no control in this experiment, and it's not really even an experiment. So how can we say that vaccines are the cause of autism? So later, The Lancet retracted this study in 2010. Now, in fairness to Wakefield, his original paper stopped short of claiming causation. Media overreaction is partly to blame for making that causal leap. However, that said, an investigation later found that he had financial conflicts of interest and falsified data even among the 12 patients he studied. So, and one other thing to know is that today Wakefield remains a vocal vaccine skeptic. But to this day, there's been no well-designed study that has found a causal link between the MMR vaccine and autism. As we know, statisticians, bad study design can lead to bias or confounding and incorrect conclusions. But what I want to talk about today is that even sometimes well-designed studies can get unlucky. You can get a good study design and get a correct conclusion, or you can get a weird sample and a weird random assignment, even in a good study design, and come to an incorrect conclusion. That's called a statistical error, and that's what we're going to talk about mostly today. So it's important to distinguish between these things. Bad study design creates bias or confounding, leading to incorrect conclusions. But error is when you have a well-designed study that gets a weird sample or weird random assignment by chance, leading to an incorrect conclusion. So let's talk about those kinds of errors and divide into two types, type 1 and type 2 errors. To discuss this, we're going to talk about a group of studies related to oxytocin. Oxytocin is a bodily hormone that has positive impacts on social behavior, i.e. promoting relaxation and trust in social settings. Scientists hypothesized that treating autism patients with oxytocin could alleviate core symptoms. So one better designed autism study than the Wakefield design was a University of Tokyo oxytocin study in 2015. They had 17 subjects who were put in a matched pairs experiment. Each subject received both placebo and oxytocin. The order in which they got those treatments was randomized, and research compared eye contact of patients on placebo versus on oxytocin. So we have comparison, we have random assignment. Replication still here is not very good, and later we're going to show another experiment that followed up on this using higher replication, and we'll talk about that further, but something to be aware of. But importantly, this study had control. You control for the placebo effect by having placebo group, and you control for confounding factors by having two treatment arms that otherwise are the same. So if oxytocin works, we'd expect that more than half the subjects to have increased eye contact relative to the eye contact time on placebo. In other words, we expect the proportion of patients on oxytocin to have higher eye contact be above 0.5, above a coin flip. It should positively move the amount of eye contact time you'd expect on the treatment. So we expect the proportion to be higher than a coin flip, higher than 0.5. So imagine in a world where oxytocin has no effect on eye contact, we'd expect only about half the patients, or a proportion of 50%, to show more eye contact. You'd be like flipping a coin between whether or not you had more eye contact on the placebo side or on the oxytocin side, given that you were randomly assigned at different times to take one or the other. No effect, so it's like half chance. Now imagine we ran a bunch of trials assuming that half chance, assuming it has no effect. By chance, with the random assignment, you might expect some variation. By chance, you might expect some trials to, because of the random assignment, happen to have more patients showing higher eye contact in the oxytocin group, even though it didn't do anything just by chance alone, or fewer than half just by chance alone. So this is a simulation of possible trial outcomes where we assume the null. All possible trial outcomes, we did this thousands of times. Most of the times, the trial results that are simulated are close to what's expected, with about half showing more eye contact. But sometimes we get, and we're since lucky, where much more than half show higher eye contact by chance alone, just due to the random assignment and what happened in that specific trial. In the actual trial, 13 of the 17 patients, or about 76, 77%, showed higher eye contact. And the p-value of that, so in a world where oxytocin has no effect, there's only a 2.5% chance of this result, or one more extreme. Only 2.5% of trials had a proportion more extreme than that one. So if we're using the rules of hypothesis testing, because our p-value is lower than the typical alpha level of 0.05, we reject the null. We have convincing evidence in this trial that oxytocin is effective because it was so unusual compared to most of the trials if you assume oxytocin is not effective. However, even though this result is improbable, it has a low p-value, its probability is very low for being this extreme, it's not impossible. It could happen, and it could happen assuming the null, given what we've seen in our distribution. It's unlikely, but it's possible. So could this result have happened by chance, even with oxytocin not being effective? Well, to test this, the University of Duke did a follow-up study in 2021. Because of the promising results from the Tokyo study, they decided to do it with higher replication, more people in their experiment. So they randomly assigned 250 subjects to oxytocin or placebo. And it turns out they found no significant difference between the oxytocin group and the placebo group. So this means that the positive result from the Tokyo study, which was much smaller, was likely an error due to chance. In other words, they got lucky with their random assignment. They did what's called a type 1 error. That's when you rejected the null, even though the null was actually true. In this case, because of the low p-value, we reject the null. And we have a 5% bar or alpha level for that rejection. That's called a rejection region. It's the amount of unusualness that we can take before rejecting the null. And 5% is our rejection cutoff. So 5% of the time, we'll make a type 1 error by chance. That's the amount of risk that we're taking, the amount of rejection we can take by chance, making this conclusion of rejecting the null. So this is the type 1 error rate. So type 1 errors happen alpha percent of the time, in most cases 5%, since we make alpha 5% in most cases. And alpha is called the type 1 error rate. So to reduce your chance of a type 1 error, you could reduce your alpha level. So in this case, we reduced our alpha level from 5% to just 1%, only taking the highest 1% to be convinced that we can reject the null. We would fail to reject in this case. However, this makes it harder to reject the null. It makes the bar of evidence higher, which can lead to what we call a type 2 error. That's when you fail to reject a false null hypothesis. In other words, you should have rejected it, but you didn't. And so here's a table describing these two errors, and this is a useful table to study before the AP exam. But hold on a second, you might be wondering, we said the Tokyo study made a type 1 error, found a significant difference in what it shouldn't have, but how do we know it wasn't the Duke study that made the opposite kind of error, a type 2 error, where it should have rejected, but it didn't? So the problem of multiple tests is the reason why we know that the Tokyo study probably had the error. The Tokyo study, they didn't just look at eye contact time. They looked at eye contact time as one outcome among many different outcomes, some of which are related to brain activity, some of which are related to social reciprocity tests across both treatment arms. And each test had the alpha 0.05 chance of making a type 1 error. And if you do this many tests, and each time you have a 5% chance of making an error, if you do enough tests, eventually you will make an error. And this is a problem for their study. So with an alpha 0.05, about 1 out of 20 samples or 1 out of 20 random assignments will get significant by chance alone. So if you take samples over and over again, you will eventually get a significant result by chance. This is called the problem of multiple tests, and the Tokyo study suffered from that problem. So instead, best practice is to do one test of a single outcome that's important from the highest sample size you can muster, as many patients in this case that you can find. Whatever result from that test are your final results. And that's what the Duke study did. And that's why we think it has more validity. So finally, one related topic we want to discuss is power. Power is the probability of correctly rejecting a false null hypothesis. It's the opposite of the type 2 error rate. Power describes correctly rejecting a false null. Type 2 error describes failing to reject incorrectly a false null. So type 2 error rate is the complement, or 1 minus the power. Note, the AP exam rarely tests that you can calculate power. Rather, it wants you to figure out the intuition and forces that affect power. So let's talk about that using a different example on blood pressure. So imagine that lowering your blood pressure by 10 or more points is medically meaningful, has a real effect on your health. And lowering it by fewer than 10 points isn't medically meaningful, just not important. Blood pressure changes should be normally imagined with a standard deviation of 21.5. You give a new blood pressure drug and placebo to a group of 20 subjects in randomized order. What is your power to detect a true average blood pressure drop by that medically meaningful 10 points? Can we detect it using the experiment that we have here? So imagine my hypotheses are the null, assuming there's no change, the average drop in blood pressure is 0, the drug is ineffective, versus looking at the alternative, there's a negative change. The drug is effective in lowering blood pressure on average for the patients. And we're trying to look for an effect size of 10, meaning the drug has reduced the blood pressure by the medically meaningful amount of 10 points. So that means we're looking for the alternative of minus 10 compared to the null, saying there was no drop at all. So first, like all tests, we assume the null. So in a world where the drug isn't effective, where the null is true, we might have a variety of outcomes where we, by chance alone, see lowering or raising of blood pressure by chance, even though the drug isn't effective. And we're going to establish a rejection zone at around 5% significance level. And in this case, that means that any sample mean with a blood pressure drop of 8 or more points, we will correctly reject the null because it will be a significant result. We've shown it lowered the blood pressure. Now, imagine that the drug is effective, that the alternative is true. Well, that means that if the alternative is true, it lowers it on average truly by 10 points. We might see an average lowering of 10 points in our trial, But it could be that because of random chance in the assignment, it could sometimes lower by a little bit less than 10 points due to random chance, or a little bit more than 10 points. And so we have a distribution of outcomes for the alternative. And in this case, only 67% of those outcomes would be correctly rejected. In other words, the power is 67%. In a world where the drug is effective and lowers it by 10 points on average, we correctly reject the null only 67% of the time due to variation by chance. So what you would want to do as a experiment designer here is you want more power. We need more power here because you want to be able to correctly reject this null hypothesis a higher percent of the time if your drug is effective. So one way to increase the power is to increase your alpha level. We establish an alpha level of 5%, which has this rejection region, but we can increase it to 15%, i.e. lowering the bar for unusualness to reject the null. In that case, our power would be higher. But here's the problem. Increasing your alpha level increases the type 1 error rate, which isn't good. It's kind of like cheating in your study, and you're more likely to make another error. Another way to do it is to raise the effect size. So in this case, we're making our drug and hoping that it can reduce blood pressure by an average of 10 points. Let's imagine that instead we create an even more effective drug that reduces it by 13 points. Now that distribution shifts, and because more of the results are further away from the null, we raise the power. The problem is that it's impossible to raise the drug's effect size without changing the drug itself. It's not something that we in statistical experimental design can do. They have to be changing the drug itself, which often as statisticians be impossible for us since we're not the ones designing the drug, we're designing the study of the drug. There's another method, which is to raise the sample size. So recruit more patients into your trial. And we know that when we raise the sample size, our estimates become more precise. In other words, these sampling distributions narrow in width. And when we do that, we see that we have a higher power because we have a more precise estimate, a more precise test. And this is usually the best way to raise the power, have more people. And the reason why, there's some intuition here. For example, imagine the drug is effective with 3 people. You only enroll 3 people in your study. You might not be as convinced that it will work for everyone. But if you had 10,000 people and you see positive results among 10,000 people, you'll be more genuinely sure it's effective in the general population because of that higher sample size. You have a more precise test, more powerful test. So recap, how can you increase the power? You could increase the alpha level. That's kind of cheating, and you're going to increase your type 1 error rate. You can increase the effect size, but that's impossible for us to do in study design. That's something that's going to be on the drug design side. But you can also increase the sample size, and that's usually the best way to do it in study design. Get more people, get more individuals, get more subjects, and that way you get a more precise estimate. So now let's move on to our discussion. Here's a cartoon from XKCD, and if you want to check out the full link to it, it'll be linked in the description. Go ahead, check it out, read it carefully. And the discussion is, what statistical problem is this cartoon pointing out? And what can scientists do to address this problem? That's it for today's Statisticians. We'll see you next time.